Arithmetic sequences. Yesterday, the homework, there will be time for questions at the end if you have any. This one should be nicer because yesterday it was just mathematical patterns in general. Could be any pattern at all. Section 2 narrows the scope to a specific type of pattern, an arithmetic sequence. An example would be 1, 6, 11, 16, etc. An arithmetic sequence is where you are adding the same number each time. So in this case, it is plus 5, plus 5, plus 5. And it's just going to keep going. And that plus 5 we call the common difference. Okay, and we denote the common difference by a lowercase d. So that is the long and the short of what an arithmetic sequence is. I'm always sure. Now, so we have this. We have our arithmetic sequence. On this page, they define an arithmetic sequence recursively, which is, we'll say, less useful. And they define it explicitly, which we will say is more useful. Just like when we talked about yesterday, why do I say the recursive definition is less useful? Because if I want the 152nd term of the sequence, with the explicit formula, I can just plug that in for n and get my answer. Recursively, I would have to know every single term that comes before it. So that's why the recursive, I say, is a little less useful. Another little notation thing is that they use just a, where we were just using A1 yesterday. I never used just A. Where the book uses A, they mean first term. Great? Outstanding. The only other thing is, why is it that we're adding the same thing each time, but we call it the common difference, where difference clearly implies what mathematical operation?
Because they ran out of vocabulary.
Subtraction. So why is it that we're adding the same thing each time, but we call that thing the common difference? That is because if you take any term in the sequence and subtract the term right before it, you get the common difference. So no matter which pair of terms you use, the difference is the same. Hence the name common, because it's always the same. Difference, because it is subtraction. The lightsaber sound definitely ends up on the recording, and AJ Taylor hates the lightsaber sound.
Yeah, Coach, I like how you were showing off the other day. Butterballs.
Here,
Hi, Tim.
part A.
Hey, Nate.
Is that sequence arithmetic?
Sure.
Yes. And you know that because there is a common difference, which is 10. Okay. The first term is 12. So let's get the explicit formula for this arithmetic sequence using the formula from the previous page that said the nth term is the first term plus n minus 1 times the common difference. So in part A, the nth term is 12 plus n minus 1 times 10, which we could simplify to be 12 plus 10n minus 10. All we did is we distribute the 10 through. So the nth term as an explicit formula is given by 10n plus 2. So this is the explicit formula. Part B. Is part B arithmetic? Hell no. What is it?
Not arithmetic. Nothing. It's a formula.
Can we write hell no on our tests and stuff? That'd be okay, or should
It's better to ask for forgiveness.
Fibonacci sequence. So somebody out there said, it's nothing. Actually, the exact opposite of nothing. It's one of the most important sequences of numbers that we are aware of.
It's every.
What are the indicated terms of the arithmetic sequence? So part A, the 110th term of the sequence that begins 5, 9, dot, dot, dot. They only have to give us the first two terms of that sequence because they do tell us it is definitely arithmetic, right? You would need more than two terms to determine if there was definitely a pattern involved, but here they tell us it's arithmetic. So the first two terms tell us, obviously, that the first term is 5, and obviously that the common difference is 4. So what is the 110th term? Using our formula, it is the first term plus 110 minus 1 times the common difference, which is what? So we get 441. Easy peasy lemon squeezy. You take the formula we had, first term is 5, plus 110 minus 1, where n is 110 because we are looking for the 110th term, times the common difference, which is 4. So this is 109 times 4 plus 5 is 441. Here, part B, we are searching for the two arithmetic means. This is a vocab thing. The two arithmetic means. That means that we have 90 and 112 are in an arithmetic sequence, and there are two terms between 90 and 12 in that arithmetic sequence. So how do we figure this out? So what we do is, looking at this, we know that the first term is 90. We know that the fourth term is 12. So using our explicit formula for an arithmetic sequence, we can say the fourth term is 90 plus 4 minus 1 times the common difference. So you get 12 minus 90 over 3 is D, which is negative 26. Now, this part right here, some of you may have been able to just intuitively figure out. You go from 90 to one number to a second number, and the third number is 12, and you know you add the same thing each time. So you know to go from 90 to 12, you've added the same number 3 times. So you do 12 minus 90 divided by 3, intuitively. Or you can use the formula, where here what we did, subtract 90 from each side, so that's where the 12 minus 90 is coming from. 4 minus 1 is 3, and we would divide by 3 to solve for D. That's why 12 minus 90 over 3 is D. Now that we have the common difference of minus 26, now we can just say A2 is 90 minus 26, which is 64, right? And A3 is 64 minus 26, which is what?
38. Yep.
Done. Here, similar to the problem we just did, except that now instead of finding the two arithmetic means, we want to find just the one arithmetic mean between 35 and 53. You could go through the process we did on the previous problem, or you could find the one arithmetic mean between 35 and 53 by taking their average, which is the arithmetic mean. Neat. Blah, blah, blah. So, we have a setup. What we have to be getting used to is this is a word problem, and you have to understand that math books, all right, sometimes I try to write word problems for tests and things that make sense. This doesn't really make sense, because not very often are you going to find any place in the world whose snowfall totals over a 10-year period form a perfect arithmetic sequence. That just doesn't happen.
That's crazy.
So,
That's neat.
accept that and just know that it is an arithmetic sequence. The first term is 21. The common difference is negative 2. We are looking for the ninth term. The ninth term is the first term plus 9 minus 1 times the common difference, which is 21 plus negative 16, which is 5. How many inches fell 2 years ago? 5 inches. Inches. 5 inches of snow. We are going to go over one problem from the worksheet, and the sequence was the worksheet that you got yesterday. This was the sequence. No. It was 1, 9, 25, 49, 81, ...
I square. I see. I got you.
The mathematical pattern is, it is the squares of the odd numbers. It's 1 squared, 3 squared, 5 squared, 7 squared, 9 squared, 11 squared, yada, yada, yada. So the first step in writing the formula for something like this, again, is recognizing the pattern. Most people I talked to found one pattern, saying it's plus 8, plus 16, plus 24. Okay? That is a pattern.
It is a pattern.
But it's not an easy one to write a formula for. Okay? But if you recognize it's 1 squared, 3 squared, 5 squared, 7 squared, 9 squared, pattern's a little bit easier. The explicit formula is the nth term is 2n minus 1 squared. The biggest thing is you have to remember how to write an odd number. An expression that definitely gives you an odd number. On the understanding that n is an integer here, if you multiply by 2, you definitely get an even number, right?
Yes.
So then your only question is, do I need to subtract 1 or add 1? Because if you take a number that is definitely even, and you either subtract 1 or add 1, you have a number that is definitely odd. So the only thing you have to decide here, for this sequence, does it need to be plus or minus? For this sequence, it has to be minus. And you determine that just by plugging in 1. 2 times 1 is 2, minus 1 is 1, and 1 squared is 1. If you had written down the formula 2n plus 1 squared, that's the sequence 9, 25, 49, blah, blah, blah. It's the same exact sequence, just starting with 9 rather than starting with 1. So these formulas, 2n plus 1 squared, 2n minus 1 squared, they are different. So you do have to be careful about it, but you have to remember, how do you write an expression for an odd number? You do that, and then you square it. Okay? On that worksheet, the problem right before this one caused a lot of issues as well. But knowing what we know now from section 2, that one should be easier, because that one is an arithmetic sequence where the common difference is 1/2. So that one's, it's all the fractions. The common difference is 1/2. So knowing what we know from section 2 now, that problem should be easier to write an explicit formula for.